All right, hello calculus students. I thought we'd look at a couple more examples where we put what we just learned, which was the polar form of a derivative, into action. So we'll start with something that we already looked at in parametric, which is for a polar curve this time. Find the horizontal and vertical tangent lines. So let's have a look at this polar curve r equals -2 cosine of theta and start with that guy. So I think first I'm just going to kind of do this without calculus, and then hopefully we can check our answer on this problem, and then we'll do another one as well. So without calculus, this should be, we just talked about some of the basic polar curves. This is another one that you should have encountered, hopefully. If you had my class, you did at least. So let's have a look at this polar curve and just graph it with our knowledge of polar coordinates. So if I think about the xy plane, and here's my x-axis, and here's my y-axis. -2 cosine theta is a circle. If you remember, r equals sine theta, cosine theta, negative cosine theta, all those things are circles. Those are circles that aren't centered at the origin, like just, r equals 4 would just be a curve that's clearly centered at the origin. This is attached to an axis. So cosine, you should realize, is the x-coordinate or the horizontal coordinate. So cosine circles are attached to the y-axis, in other words, in the horizontal direction. If it's negative, that's a polar reflection, so that's going to flip it this way. If it was sine, it would be attached to the x-axis in a vertical persuasion. If it was negative sine, it'd be reflected this way. So negative cosine, I think, is a circle that looks something like this. And that 2, what that does is that tells you that the diameter of this circle is 2, or in other words, it goes out 2 in that direction. So let's just have an idea of what this problem is already asking us for. We can pretty much just visualize it here. Looks like probably at -1, we're going to have a tangent that's horizontal on the top and the bottom. Looks like at x equals 0, we'll have a vertical tangent, and then over here at 2, we'll have a vertical tangent as well. So hopefully that's what we should get when we do it with our calculus approach, and then we'll be pretty confident about it. We'll move on to an example where we can't just picture the graph simply like in this problem. Okay, so let's try not to use memorization here. Move this r equals 4 out of the way. That was just a counterexample. So let's start with our parameterization, or turning the polar coordinates into parametric, and we'll just employ that approach. No memorization required. So what is polar? So x is r cosine of theta, correct? And y is r sine of theta. We just talked about and reviewed those polar conversion equations. Well, that kind of already has it set up as parametric equations as well. The only difference is you need to now think about r being a function of the parameter theta, and then you just multiply that by the cosine to get your x parametric equation. And to get your y, you think about r being a function of theta, and you multiply by sine, and you'll get your y parametric equation. And of course, r for this problem is right over here. So now we can find the derivative. So we'll go dy dx is going to be, remember, if you have parametric equations, so if you haven't done parametric and you're watching the video, you want to go back and do some parametric assignments first. But that's going to be dy dt over dx dt. And you know what? My parameter in this problem, and in all polar problems pretty much, is going to be theta and not t. So this should really have been a theta. Let me fix that really quick. There we go. And let's get a theta in there for our parameter theta. Okay, so now we just need to take the derivative of y with respect to theta. Now, in class, and also a couple times when I was trying to go really fast at the end of the hour, I got mixed up on this, so that might be something that happens to you as well. Make sure you're clear that it's dy d theta that I'm going to put on top, right? That's from this guy. So remember, r is going to be for us, so that's what it was in general, right? Let's write what it is for us. F of theta, or r, for us is -2 cosine, and then if you multiply by this other cosine, you're going to get cosine squared, right? And for us, this is going to be -2 cosine theta, and then times sine of theta. So notice, if you didn't recognize that squared, you could have just gone ahead and shot right into a product rule. Right here, same kind of thing. You could just shoot straight into a product rule. I think I'm going to make this a little easier on myself by using some identities. I mean, you can see that in this last unit, identities are king. If you see 2 sine cosine or 2 cosine sine, that's, remember, the sine of the double angle. Now, if you don't recognize that, of course, you can move on and just use the plain product rules. But this way, I'm going to have a little bit less work to do. So dy d theta, I'm going to look at y, not x, and take the derivative of that. So the derivative of sine is cosines. This is going to be negative cosine of 2 theta. And my chain rule says times 2. Alrighty. And then on the bottom, I'm going to have to take the derivative of this guy. So remember, I like to write that as cosine of theta squared. So I'm going to say negative 4, because I bring down that 2, and then I go cosine of theta left alone inside to the 1, and then times the derivative of the inside with my chain rule. So that's negative sine of theta. Okay, so I could simplify this if I want to. Looks like we have negative, negative, negative. I could get rid of some negatives here. I'm just going to go negative cosine of 2 theta on top. And then on the bottom, it looks like I have negative, negative is positive, and 2 over 4 reduces to 1/2. So that's going to be 2 sine of theta cosine of theta, and it looks like I'm going to get to use my double angle identity again. So on top I have negative cosine of 2 theta. You could of course do these problems differently if you don't recognize your identities from trigonometry, but they sure do make it easier. So there we go. That's kind of fairly reduced. You could of course write that as negative cotangent of 2 theta, since you've got a 2 in the top and bottom, but I don't think I'm going to this time. So let's see, what do we want to do? We wanted to find where it was horizontally and vertically tangent. So horizontally tangent means, of course, where the slope or the derivative is equal to 0. So that's going to be where the top is 0. So where that's going to be 0 is where negative cosine of 2 theta equals 0. So I think I can just divide the negative 1 to the other side, so I'll get 0 equals cosine of 2 theta. Then I can operate on both sides with my arc cosine, or my inverse cosine. See that that equals 2 theta. Go to my unit circle for where is the cosine, 0, or in other words, what angle, or in this case, what x value has a cosine of 0, and that's going to be up here and down here, I think, right? That's where the x coordinate is 0. So, let's see. So that's going to be at pi over 2. For one of them, we'll just start with that, see if we can get one of our lines that we already know about up here, and see if it checks out. So we can divide by 2, and we'll get pi over 4 equals theta. Okay, so that's theta. I really need my line, and if I'm looking for horizontal, I think it's going to be a y equals. So you could stick this theta equals pi over 4 into x and to y. I'm really going to focus on y. So you get the point or the line. I'm just going to focus on y. So I'm going to say y then. You know what? I think I'm going to do that in a different color just to help you keep track at home. So that means y is going to be what? So we could look at right here, we could look at right here, we could look all the way back down here. So I'm going to look all the way down there. So that's going to be negative sine of 2 times pi over 4, that's 2/4, that's 1/2. So that's going to be negative, and sine of pi over 2 is the y coordinate up here. So that's going to be 1, negative 1. So that says y equals negative 1. Is y equal to negative 1 one of my tangent lines? Yes, it is. That's this guy right here. So it looks like we're doing good. So we've got one of our horizontal tangent lines. There's another one. Where can we get that from? Well, going back to this, remember this worked or this worked. This is what the principal arc cosine value is going to be because it lives in these two quadrants. But of course, the actual values that could satisfy the arc cosine of 0 would be plus pi k. So there's an infinite number here. So I'm going to say the next one would be 3 pi over 2 is 2 theta. So if I divide by 2 there, I'll get 3 pi over 4. So that looks like another productive spot that I should check. So I'm going to take this guy over here and say y equals negative, from up here in the y parametric equation, the sine of 2 times 3/4. That's going to be 6/4, which is 3/2. So there we go. So negative sine of 3 pi over 2, that's down here. Sine being the y-coordinate again, so that's negative negative 1, which is 1. So that says another tangent line spot, or another spot where at least the slope of the derivative is equal to 0, which is going to be a horizontal tangent line, is up here, and I think that's this guy. Now if you're asking yourself, are there more horizontal tangent lines that we missed, maybe our graph is just wrong or something, you could of course check your next theta answer by going back over here and saying, okay, pi over 2, 3 pi over 2, the next one will be at 5 pi over 2, and working this out, but I think you'll get that that's just going to be a copy of this line right here. So I'm not going to get any more unique ones. If you don't believe me, go ahead and check the calculation. Alright, let's do our vertical tangent lines before we're done with this problem and move on to another example. So I'm going to switch colors to black here and say, where is dy dx undefined? So that's of course going to be where the bottom is 0, so that's where we have 0 equals the sine of 2 theta from right here. Okay, so that's going to be the arc sine of 0 is equal to 2 theta. So we go over here to our unit circle and say, where is the y-coordinate, or the sine, equal to 0? I think that's going to be here and here. So I'm going to say 0 equals 2 theta. So that says theta equals 0. So if I put theta equals 0 in, I could of course put this in for x and for y. You could do both. That'd be fine. Then you'd find the point that has a derivative that's undefined, or in other words, a vertical slope. But I think I'm really just interested in the x, so I'm going to focus on the x, because that'll give me my x line that I'm going to get for vertical. So I'm going to say x equals negative 2 cosine of, what was our angle here? 0. And negative 2 cosine of 0. Oh, and I need to square that. So cosine squared. So what is the cosine at 0? Well, at 0, cosine is x. That's going to be 1. So that's negative 2 times 1 squared. That's just negative 2. So x equals negative 2. Is that one of our tangent lines that we were thinking about? Yeah, that's this one right here. Nice. So hopefully the next answer will be the other one. So now if we go over here, at pi, then we're going to get the arc sine. I'm just going to do this down below and clean it up in a moment. So let's go with a different color here, shall we? I'm running out of colors, so we're going with green. So I'm back right here, and the inverse sine of 0, we're going to say, is also equal to pi. That's 2 theta. So that says theta equals half pi. So now if we take that and we go and plug it up in, just like we did with this, we're going to say that x equals negative 2 cosine of, what was it, pi over 2. We're supposed to square that. So that's going to be negative 2 cosine. What's the cosine right here? Pi over 2. That's going to be 0, isn't it? Yeah, cosine is x. So that's going to be times 0 squared, which is going to be 0. So is x equals 0 another spot where we have a vertical tangent? Yep, it sure is. So that looks like that problem turned out successfully. Alright, I'm going to take a short break here and we'll come back and do another one where we can't see the graph in advance. So I'm back. We're going to look at one more example of finding horizontal and vertical tangent lines. This time the curve isn't necessarily a real basic. It's a fairly basic polar curve, but it isn't one that you should necessarily just be able to picture automatically. So I've written down my polar conversion equations, x equals r cosine, y equals r sine. I've said, oh, r is this f of theta function, so I stuck that in both spots. And now you can distribute before you take your derivative, or you can leave it alone. I think I'm going to do some simplification first. How much you do kind of depends on the problem. It takes experience to see what to do. So I'm going to distribute the 2, and also the cosine of this problem. I'm just going to do that at the same time. So I think I get 2 cosine here. And if I distribute the other one, I'm going to get minus 2 cosine squared. And since we're going to be taking derivatives, I'm going to write that like this, 2 cosine squared. All right. On the bottom, you can also distribute, and you'll get 2 sine theta. And if you distribute down there, you're going to have minus 2 cosine theta sine theta. This is obviously the sine of double theta, if you know your identities well at all. But I think I'm going to leave that off this time. So I've kind of looked ahead and seen what was going to happen. If you wanted to use an identity, it might be a good thing to just try right now. All right, so let's do the derivative, dy dx. So now, this is a spot where I have always a difficult time not making a mistake. So on top, I should do dy d theta. Make sure you pick the right equation. That's this one. So I'm going to do dy d theta on top. So if I take the derivative of this guy over here, I get 2 cosine, right? And then I've got to do a product rule. So I'm going to say minus 2, and I'm going to be doing a product rule. So the first times the derivative of the second is going to be another cosine, plus the second, which is sine, times the derivative of the first, that's going to be another negative sine. Alright, I can simplify that in a moment. So now I'm going to do dx d theta. I think that'll be a little easier. Derivative of 2 cosine is going to be negative 2 sine. Alright, this guy, if I bring the 2 down, it's minus 4. Leave the inside alone to the 1 power. Derivative of the inside with my chain rule is that. Okay, let's simplify this guy. So we're going to have 2 cosine. My hand's getting a cramp. Alright, so 2 cosine, then we've got minus 2, and then up here we've got, let's see, cosine squared minus sine squared. Alright, so there's that. On the bottom looks like I have minus 2 sine, and then plus 4 sine cosine. So at this point, you're really focused on what you're trying to do with this derivative. I'm trying to find the horizontal and vertical tangent spots or locations. So I think I'm going to look at the bottom first. I'll try to find any vertical places first. We'll see if we can find any of those. So I'm going to go to the bottom first. So I'm going to do all the bottom calculations in red, just to clarify here for you. All right, so we're going to see where the bottom is 0 first to find any spots that are vertically tangent. So you've got to do what you can do. Looks like there's a double angle identity I could use here, but these also share a sine of theta. So you know what? I'm going to factor that out. I'm going to say minus 2 sine of theta, pull it out, and I get 1 minus 2 cosine of theta. And then I can see where the sine of theta is equal to 0 for this factor. Make that a bullet point. And then I can see where 1 minus 2 cosine of theta is 0 for the other. Of course, that minus 2 really doesn't matter for this one. So I'm going to get theta equals the inverse sine of 0, which is going to be, let's draw that. That's going to be, where is sine 0? That's going to be here and here. So I get theta equals things like 0, pi, 2 pi, etc. Alrighty. So now let's do the other one. That says cosine of theta equals 1/2 if you move that stuff. So then that says theta equals the inverse cosine of 1/2. That's going to be a triangle, right? It's going to be adjacent, hypotenuse, square root of 3. Get a different color in here. That means this must be 60 degrees. So we must have theta equals like pi over 3, and then like down here at like negative pi over 3 or 5 pi over 3, whatever you got going on. Okay, so I'm just going to write out those first couple and see if we have any more. Probably not. Alright, so those are our possible places where we could be vertically tangent. So I'm going to throw them back up in here in X and see what happens with them. So I'm going to do that in black. So I'm going to have X equals, let's see, R cosine of theta. Oh, I should really just use this thing up here, right? So it's going to be like, for instance, for 0. I think 0 is an interesting case on this one too, but let's just do it. So that's going to be 2 times the cosine of like 0 minus 2 times the cosine of 0 squared. Let's see, cosine of 0 is like, you know, right here. We're thinking about all our different spots. So that's going to be 1 over here. It's going to be -1, etc. So that's going to be what? 2 minus 2, and then cosine of 0 is 1, squared is 1, so that's just 0. Okay. So that says x equals 0 might be a possible spot where we get a vertical tangent line. All right, let's try pi and see if that's any different. So that's 1. Now let's do it with pi. So it's going to be 2 cosine of pi minus 2 cosine of pi squared. So that's going to be 2 cosine there is -1, and I've got minus 2 cosine of pi is -1 squared. So that's going to be minus 2, that's -4. So that says x equals -4. Looks like it's another spot where we're going to have a vertical tangent line. Okay, let's see about another spot. So now I've got x equals, what do we say, 2 pi? Okay, so we could do 2 pi, so that'd be 2 cosine of 2 pi minus 2 cosine of 2 pi squared. That's going to be 2 times 1 minus 2 times 1 squared. That's going to be 2 minus 2. Again, that's giving me x equals 0. So that's redundant, so I'm just going to erase that. So this must not be necessary right here, and neither is any of this. That is redundant. Okay, now let's look at our other one. So now I'm going to go here, and sorry, my computer's making a lot of noise. It just is. So now we're going to look at pi over 3 and toss that in. So we got that one. I'm going to make some nice bullet points here. Okay, so now pi over 3. So that's going to be x equals 2 cosine of pi over 3 minus 2 cosine of pi over 3 squared. So that's going to be 2. We got pi over 3 right here, right? The cosine is 1/2. Minus 2 times 1/2 squared. What's that going to be? That cancels to 1 minus 2 over 4 is 1/2, so that's 1/2. So I see another tangent line that's vertical. Probably going to happen at x equals 1/2. Okay, and then we could try 5 pi over 3 and see if we get something different there. This is kind of out of control. It's a long example, but that's okay. So I'm going to get 2 times the cosine of 5 pi over 3 minus 2 cosine, oh my, cosine of 5 pi over 3 squared. So 5 pi over 3 cosine is going to be the same thing, isn't it? Like down here, at 5 pi over 3. So that's going to be 2 times 1/2 minus 2 times 1/2 squared. Okay, yeah, that's going to be the same thing, right? That's going to be x equals 1/2. So it looks like that was redundant as well. So far looks like I have 3 vertical tangent lines at 0, -4, and 1/2. So we'll check that at the end. But I want to also do my horizontal tangent lines. So I'm going to go way back up here, and I'll focus on doing horizontal in green. So horizontal tangent lines are going to, of course, come from where the derivative is 0 or where the top is 0, in other words. So let's go and look at the top and put it down here. So where's the top going to be 0? So I've got some choices. I could make this into cosine of double theta. If I wanted to factor like the bottom, though, I think I want to make a different choice. So I'm going to go 2 cosine of theta minus 2. And I think I'm going to change this into another version. So let's say that cosine squared. Do I want to change it into cosines or sines? I want to match this cosine. So I'm going to change this sine squared into 1 minus cosine squared of theta. So that's going to be cosine squared of theta minus 1 minus cosine squared of theta. So this is going to be 2 cosine of theta minus 2. The minus minus gives me plus, so that's 2 cosine squared of theta minus 1. Of course, you just might know that identity automatically. I don't know what you guys know, whoever's watching the video. Okay, so then we're going to distribute the 2, and we'll get 2 cosine of theta minus 4 cosine squared of theta. -2 times -1 is 2. Alright, so that looks like a parabolic thing, which we probably want to factor. So I'm going to turn it around, and I'm going to take, looks like they all share 2 as well, so I'm going to take 2 out. So in fact, you know what? I'm going to take negative 2 out. So I'm going to say negative 2, and then what's left of this term is going to be positive 2 cosine squared. Okay, crack my knuckles here. And then if I take 2 or negative 2 out of this one, then I have minus cosine left. If I take negative 2 out of that, I'm going to have minus 1 left. Okay, that looks like it's something that I can factor. So you could do this with guess and check, or you could use the little longer procedure where you do like 2 times negative 1, if you remember what I'm talking about there. This one's pretty easy to guess and check, though. So I'm just going to say it factors into 2 cosine times cosine. That'll be my 2 cosine squared, and 1 doesn't give you very many options, so it's going to be 1 and 1. The only question is, what signs do we want? Well, we want negative cosine here, so we want it like this or like this. I think it's going to be like that. Let's double check. So if we think about expanding this back out, it would be 2 cosine squared, check. We'd have negative 2 cosine and positive 1 cosine is negative 1 cosine, great. And then 1 times negative 1 is negative 1. Awesome. So now I've got it factored, and I can check where it's 0. Yay! So that's where 2 cosine of theta equals negative 1 for this one, or where cosine of theta equals 1 for this one. Okay, so if I operate here, I'm going to get theta equals the inverse cosine of 1. In other words, where is the x-coordinate? 1, so that's going to be here, right? Just there. That'd be negative 1 there. So that would be like theta equals 0. I think we've seen this before. Complication? Let's worry about it in a moment. So here we have cosine of theta equals negative 1/2, so that's where theta equals the inverse cosine of negative 1/2. So that's going to be, let's scroll down a little bit, that's going to be, cosine is negative over here, so adjacent hypotenuse, this is square root of 3. So then this is 60 degrees, so this is going to be, so let's remember that one. So then this one's going to be theta equals 2 pi over 3. And also I think at 4 pi over 3 is another possibility, so I think we want to check both of those at least. Alright, so let's plug these in. Now we were, of course, where did we get this from to begin with? Let's see, remember it was right here. And where was that from? That was from up here, right? That was the top, or where we thought our horizontal tangent lines might be. So remember, we want to go all the way back to y equals and stick this in and see what happens. So let's remember, it's 2 sine theta minus, and remember this is another way to think about this, is 2 sine theta minus sine of 2 theta. So it might be easier to think about it in that version. It doesn't really matter though, so I'm going to remember that down here. So I'm going to need to go y equals 2 sine, let's go 0 first, right, this one. 2 sine minus, wasn't it sine of 2 times 0, so that's 0. So the sine of 0 is, of course, the y-coordinate right there, which is nothing. So that's 2 times nothing minus nothing, which is nothing. Interesting. So do we have, let me get rid of that, sorry. So at y equals 0, do we have a horizontal tangent as well? Interesting. So see up here, it said at x equals 0, we had a vertical tangent. Here it says that y equals 0 is actually a horizontal tangent line. I don't think it can be both of those things at the same time, so I'm guessing that this is not true. And that also means that this is not true, because x equals 0 and y equals 0, both the top and bottom of this right here are 0. That might be an issue. We'll see what that looks like when we get to actually looking at the graph. So I'm not sure about that one, but it looks like something fishy is going on. Let's check these other ones. So here we're going to have 2 sine of 2/3 pi minus sine, remember I changed it into 2 times 2/3, or 2 theta. So that's going to be 2 times the sine of this guy, which is root 3 over 2, right? And then minus the sine of 4 pi over 3, that's going to be down here, right? So that's going to have this guy being a negative. So, oops. So that's going to make this guy, just write it in there, it's going to be negative square root of 3 over 2, right? So simplify, this cancels, get square root of 3 plus square root of 3 over 2. What is that? Well, remember, this was y equals. So can we go magic clever 1? So times 2 times 2. So that's going to be 2 root 3 plus root 3 over 2. That's, in other words, 3 root 3 over 2. So that's what y looks like it's going to be. I'm going to stick that in my calculator later. But we'll see if it kind of looks right once we get to that spot. So, alright. So let's go and do the other one. So we did that one. Let's do this one kind of down a little bit lower. So that's going to be y equals 2 sine of theta minus sine of 2 theta. So it's going to be 8 pi over 3. Alright, that's going to be 2. The sign down here we decided was negative root 3 over 2 and minus 8 pi over 3. Where's 8 pi over 3? So that's, let's see, 3/3, 6/3, and back to 2/3. So it's going to be back to there. Okay, so that's going to be minus square root of 3 over 2. So let's simplify that. And we're going to get what? This cancels again, so we're going to have negative square root of 3 minus square root of 3 over 2. It's going to simplify very similarly to the last one. Do a clever 1 right there, and you're going to get negative 2 square root of 3 minus square root of 3 all over 2, which is negative 3 square roots of 3 over 2. That is a different answer, and let's see what those look like as decimals, because I am really curious. So I'm going to go to my calculator and pull it up for a moment here. I'm going to clear out any equations I have. And let's see what that is. So we've got 3 square roots of 3 over 2, right? So that's going to be 2.59. Before we forget, let's just write that down right here. So y is approximately 2.59. It's looking like that's where we're going to have a tangent. Okay, now let's actually go to the graph and see what we got, and see if it makes sense with what we had. So, time to go to polar mode. So I'm going to go down here to polar mode. Change it from parametric to polar. Go to y equals then. And what was our polar equation that we were investigating all that time ago when we started this problem out? Was 2 times the quantity 1 minus cosine theta. Alright, so I'm going to make sure my parameters doing good. Go to my window. I probably want to go back a ways just in case I see more of it. Maybe like negative 2 pi. Alright, let's try that. It looks like my window's a little too small, so let's go down here and make this like 5. It looked like it went backwards. I'm going to go negative 10. And we'll go negative 10. Let's see what that looks like. Okay, I think I went it too big. Let's go, let's just go negative 5 and negative 5. That looks like a nice cardioid. Now let's go and look at what we got for results. So it looks like on here that we have 2 horizontal tangents, and then vertical we have 1, and then this one looks like it's like in the same spot, so that also looks like 1. So what did we actually get? Let's remember. Well, we had this weird thing, remember, that happened at 0 where we got a horizontal possibility, then also a vertical possibility. Vertical and horizontal, I should say. So look at that right there. Isn't that like a cusp? I think that's a cusp. That should make sense because it wasn't strictly horizontal or vertical. It was like 0 over 0, so it wasn't decidable which one it is. So that makes sense, I think. Then for the other vertical ones we got x equals negative 4. That looks good. Negative 4. Yep. We got x equals 1/2. That's 1. Could that be 1/2? Yeah, I'm guessing so. We could, of course, trace on our curve for a while. See if it looks like it's close to a half. Oh, right there, it's on it. And then it goes back. So yes, that's 1/2, and you can see that's tangent in 2 locations, coincidentally. So it looks like we did that part right. And then down here, the only other horizontal tangents we got were this 2.59 through root 3 over 2 thing and its negative counterpart. It does look like we have some symmetry. Let's just kind of scroll around and see if we get like something close to 2.59 for the y. 2.55, 2.598. Totally, that's got to be it. That must up there be 3 square root of 3 over 2. Nice. And then down in the bottom you can see that there's another one that's going to be this one at negative 3 square root of 3 over 2. All right. Before we leave off, I wanted to talk about one more thing, so let me pause and we'll talk about. So before we leave off in this video, I wanted to do one last example that I think you'll kind of need to do a few problems in your assignment and pretty important for this kind of thing. So this is the theorem that talks about tangent lines at the pole, especially in the case where there's more than one. So let's just kind of walk through this part of the book step by step. So it says the theorem from before has an important consequence. So that's just the one where we discovered the derivative of polar graphs. So suppose the graph of r equals f of theta, that's what this says right here, passes through the pole. So we're assuming that it passes through the pole. So that means, and they're saying that at some value of the parameter or the theta equal to some specific alpha angle, let's just say. We're also assuming that the derivative at that angle is not equal to 0. You'll see why we need that in a second. Then the derivative, and here's our derivative that we're not going to memorize or anything like that, but that came from the product rule of the top and bottom in parametric. It says the derivative reduces to this, so why does this become 0? Well, remember, the assumption for this theorem, so what you assume is that if f of alpha equals 0, so if f of alpha equals 0, then it's you're assuming that f of alpha equals 0. That's what it means to go through the pole. You're saying that the value of the function at that specific alpha equals theta spot is equal to 0. So that's what makes this and this go to 0, which of course kills those off as well. So then you can simplify it. Now you can see why you need this condition in here as well, because if that was equal to 0, then it would screw it up right here. But since it's not equal to 0, we're assuming that as well. You know, if it is equal to 0, you can't apply this theorem. But if it isn't equal to 0, then you can apply this theorem, and the derivatives cancel right here. So you just get sine of alpha over cosine of alpha, which of course simplifies to tangent of alpha. So the book says, so the line theta equals alpha is tangent to the graph at this point. Now let's remember here that we're in polar coordinates and not Cartesian. So this is a radius of 0, so we're at the pole, and an angle of alpha, which we're saying the parameter theta, or the angle polar coordinate is. So that means that, you know, let's just visualize. We've got a nice picture over here. But so if we think about an angle, we're calling it alpha, right? We've got that specific alpha. Remember, so this says the derivative or the slope of the tangent line is equal to tangent of alpha. What is really tangent of alpha? Tangent of alpha in polar coordinates, or tangent of theta, is really just equal to y over x, or kind of like the rise over the run, right? So if you think about that, then really in polar coordinates, this angle is really just a line. So this thing up here, this line, remember what we talked about when we looked back at basic polar graphs. We said like r equals 3 is a circle centered at the origin, right? We said theta equals like some specific number like pi over 3. It's going to be some line that always has an angle or maintains an angle of 60 degrees. This is just like that, except we're maintaining an angle of theta equals alpha. So there you go. If the derivative has a slope equal to the tangent of alpha, then that's just basically describing this line. So that's how they got here. I think that's a little bit mysterious. And I think the reason it might be mysterious is you're not thinking about polar coordinates, you're still stuck thinking about regular traditional Cartesian coordinates. So make sure you're thinking about polar coordinates, and then you'll realize that this is just the polar version of a line. It's just a line that maintains that same rise over run, that same, if you want to think of it as 60-degree angle or whatever, that same alpha angle. So that's the way we write a line in polar, is like this. Okay, so now let's actually talk about where the theorem is useful, where you'll need it in your assignment, for instance. So if that's true, if it goes through the pole, that's what this condition says, and this condition says There's no sharpness at the pole, basically. No sharp corner or cuspness like in that last example. Then theta equals whatever the angle is tangent at that spot. So it says this is useful because it shows that the zeros of a polar function can be used to find the tangent line at the pole. So that's really nice. So a polar curve like this rose curve over here, 2 cosine of 3 theta, you can see has a few different tangent lines at the pole. It's clearly got this tangent line and also this tangent line. So how do you use this theorem to help you? Well, you say, all right, so if that's true, then that's going to be true. So you can see down here that in fact there's 3 tangent lines to the pole. There's also this one, right? For this curve, if you set it to 0, and in other words, see what angles alpha make it 0, look at the zeros, you'll also be able to find the tangent lines at those spots. So that's the great part about this theorem. You can translate translate zeros into tangent lines at the pole. At the pole, not somewhere else. Okay, so of course you could solve for this. They just give us some answers, but you could solve, right? Let's find a couple of those. Cosine of 3 theta equals 0 over 2. That says 3 theta equals the inverse cosine of 0, because 0 over 2 is 0. Whereas cosine 0, that's going to be like right here and right here. So that would say 3 theta equals pi over 2. So one of those places should be pi over 6. Bam. Another one would be 3 theta equals, what's this guy down here, 3 pi over 2. So if we do that, then we get theta equals 3 pi over 2 times 3 is 6. That's going to be theta equals pi over 2. Bam. And you can see that those match right here. So at the theta equals pi over 2, we get this one. There's that one that we just did. And theta equals pi over 6, you can probably guess is this one. So then where else could this be true? Well, we could keep going. So we could say then around again, that would be 5 pi over 2. So let me just do that one up here. So that would be 3 theta equals 5 pi over 2. So then that would be theta equals 5 pi over 6. Is that looking like this guy? Oh, no, that's the pi over 6 one. This guy right here is 5 pi over 6. You can see that angle is 5 pi over 6. So there you go. So this shows you how to translate zeros into tangents at the pole. I think I've done enough drawing on this one. So I'll see you next time, and we'll continue looking at some polar calculus then.